Hi there. So this is part 2 of our lecture on determinants. Okay, so we got through the 9 properties of determinants. We had a couple more examples that we wanted to look at. At the bottom of this page, compute the determinant of the following. Okay, this is the identity matrix. So the determinant of any identity matrix is 1. Okay, this is the determinant. This is a identity matrix of a 4x4 with a row swap. Okay, so we're swapping the rows 1 and 3. Okay, once you place row 3 as 1, 0, 0, you have 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1. So this is an identity matrix with a 1 row swap, and under property, let's see what it is. Property 2, the determinant of the row swap will be negative, the original. So the determinant of this matrix is going to be not 1, but negative 1. And lastly, the determinant of this is 0. Okay, we said under property number, let's see what it would be, 4. If any of the rows in the matrix are all 0, then the determinant is 0. There's a row that's 0. There's also a column that's 0. So that would have made that true as well. Okay. This is the last page I want us to look at. The determinant of a 4x4 matrix. A is a 4x4 matrix, sorry. The determinant of A is 7. What is the determinant of 5 times A? So, just keep in mind when you do this problem, the property, let's see, where was it? The scaling property. When you scale a row of a matrix, the determinant of the new matrix is going to be that scalar times the determinant of the old matrix. Now, remember what you're doing here. You're taking a matrix that's 4x4. So A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Okay? And by scaling it by a factor of 5, this new matrix is going to be 5A, 5B, 5C, 5D, all the way up to ... 5M, 5N, 5O, and 5P. So every element in every row is going to be multiplied by 5. So it's not just the first row that gets scaled, it's the second row, the third row, and the fourth row. So if you're told that the determinant of this matrix A is 7, then the determinant of 5 times this matrix A is going to be 5 times 5 times 5 times 5 times 7, or 5 to the 4th times 7. Okay? So that was a tricky one, and you had to take advantage of the fact that they're telling you it's a 4x4 matrix to be able to solve that. And the next example, they give you a 4x4 matrix and ask you to compute the determinant of it. Okay? For this one, take a look at column number 3. A bunch of zeros in it. Okay, so the determinant of that matrix is going to be, well, you're going to have, it's the determinant of 4 3x3 matrices, but three of the 4 3x3 matrices are going to be multiplied then by 0. Now, it's only the third one that's not. And so when you cross out the row and the column that the third one is in, you're left with the matrix 2, 3, 1, 4, 7, 3, and 1, 2, 4. 2 and 4. Now, what are the coefficients, positive or negative? This is what row 1, column 3. So row 1, column 3 is a 4, so that's a plus. So that's a plus. Next one's minus. Next one's plus, and negative 2 times that. And the final one is a minus. Okay, and it really doesn't matter what goes here, here, or here, because the determinant of those 3 by 3 matrices are again going to be multiplied by 0. So this 4 by 4 determinant now is equivalent to computing the determinant of a 3 by 3 and multiplying it by negative 2. All right. So, what does that end up being? We have negative 2 times the determinant of this 3 by 3 matrix. Expand across any row or column you so choose. There's not one that's any better than the other, so when it doesn't matter, I just multiply across the top row, or expand across the top row. So it's a positive 2. Cross out that row and column, you have 7, 3, 2, 4, minus 3 times row and column, 4, 3, 1, 4, plus 1 times last row and column, 4, 7, 1, 2. All right, let's see what we get. Negative 2 times 28 minus 6, so that's 22. Minus 3 times 16 minus 3, that's 13. Plus 1 times 8 minus 7, so that's 1. So this is 44 minus 39 plus 1. 44 and 1 is 45, minus 39 is 6. This is a negative 12. All right. So why do we use determinants? Well, we use determinants for a lot of different things. What we're going to use next is Cramer's rule, which is solving systems of equations. So, get rid of this sheet of paper. Cramer's rule, if the determinant of A is non-zero, okay, then the solution to AX equals B is the vector X with components x1, x2, all the way up to xn, where each of the entries of that vector is the determinant of BK divided by the determinant of A, where BK is the matrix A with the kth column replaced by the right-hand side. Okay, so that's a mouthful. Let's see what that means. So, here's the coefficient matrix. Okay, coefficient matrix 5, 3, 6, 2, 4, negative 7, 2, 5, 9. Okay, and that's the denominator. Let's see if I'm pointing at, I'm not pointing at anything that's in the screen. That's the denominator of what our solution is for the kth entry of our vector. So I've taken the liberty to compute the determinant of A, our denominator here. It's 271. Okay, I'm only doing this for the purpose of brevity and so that you don't have to watch me do a lot of computations. So now we look at B1. Okay, B1 is the matrix A, so it's this matrix right here, with the first column deleted and replaced by the right-hand side of our system of equations. So instead of 5, 2, 2, we replace it with 3, -1, and 4. That's the right-hand side. That's the b part of ax equals b. And when you do that, you compute the determinant of b1 to be 30. So therefore, you can conclude that x1, the value of x1 that helps solve this system of equations, is the determinant of b1, 30, divided by a, 271. Okay, what about x2? Okay, well, to find x2, what you do is you take, get rid of this now. You take the matrix A and you delete row 2, or column 2, and you replace it with the right-hand side vector, that's 3, -1, and 4. And this is the matrix B2. Compute the determinant of B2. According to my calculator, it's 59. So that means x2 is the determinant of B2, that's 59, divided by the determinant of A. That's 271. And lastly, to compute x3, x3 is going to be the determinant of B3 divided by 271. B3 is the matrix A with the third column deleted, replaced by the right-hand side, 3, -1, and 4. Okay, just to remind you, 3, -1, and 4 is coming from this system of equations that's right here. It's the right-hand side. And that gives us, according to my calculator, 81. So the solution to the system of equations is x1 equals 30 over 271. x2 is equal to 59 over 271. And x3 is equal to, what was that number? 81 over 271, sorry. Okay, imagine how frustrating that would be if you were to do Gaussian elimination, row reduction, all of that. That would take absolutely forever to come up with those values. And again, what we're doing here is we're taking advantage of the fact that we're solving the system ax equals b. B is the vector 3, 1, 4. X is the vector x1, x2, x3. And A is the coefficient matrix 5, 3, 6, 2, 4, -7, and 2, 5, 9. Okay? All right. So I'm not going to show you a bunch of examples of Cramer's rule because Cramer's rule is only as difficult as computing a set of determinants. So that's the end. That's the last bit that will take you through the problems in section 3.6. And you should be good to go for our midterm on Friday. If you have any questions, please feel free to stop by office hours or shoot me an email. Be more happy to help. Take care.